When you type a prompt into an AI model, the answer seems to appear out of thin air. We call the infrastructure supporting it the cloud, a word that makes computing sound weightless, as if it is floating above the physical world. But the cloud is incredibly heavy. That digital answer is actually generated inside warehouse-sized buildings packed with servers, cooling pumps, and thick fiber optic cables. Take a look at this chart tracking global electricity demand. The flat line at the bottom represents standard power growth across the world, rising slowly over many years. But this sudden vertical spike shows the projected electricity demand from AI data centers, which the International Energy Agency expects to nearly double to roughly 950 terawatt-hours by 2030. Securing advanced computer chips is only one half of the equation. Without a constant, reliable flow of electricity, the most advanced silicon in the world is effectively a collection of silent machines. AI represents a massive new layer of heavy industrial demand, built directly on top of our existing physical economy. To understand this scale, trace a single AI request backward from your screen. The prompt travels through the software application, down into a server rack, and eventually into specialized high-performance computer chips. Because these specific chips perform billions of calculations per second, they run exceptionally hot. Cooling them requires massive industrial equipment. To an electricity grid, an AI data center functions as a heavy manufacturing plant. The Department of Energy notes that future AI data center campuses could require up to a gigawatt of power to operate. A single 1 gigawatt complex running at high capacity consumes billions of kilowatt-hours annually, roughly the electricity profile of a major industrial city. A tech company can spend billions designing the smartest AI model and purchasing the fastest silicon, but without the physical electricity to run the machines, those assets produce absolutely zero revenue. Getting that power to the data center requires navigating the electricity grid. The current must travel through high-voltage transmission lines into electrical substations and industrial transformers. Software scales in months, but physical infrastructure scales in years. Wait times for critical grid components like transformers have doubled. In advanced economies, getting the permits and building new transmission lines can take anywhere from 4 to 8 years. This flow diagram shows what happens when digital speed collides with industrial reality. The thousands of digital data center nodes on the left represent planned projects, and they are all choked at this narrow grid connection point. By early 2026, more than 2,500 gigawatts of generation and large load projects were stalled in these connection queues. Because of this bottleneck, tech companies are abandoning traditional strategies, migrating away from skilled talent pools outward to isolated utility corridors with spare power capacity. Land and software engineers are no longer the primary constraints. The ability to legally and physically connect a building to the electricity grid is becoming a highly valuable, highly scarce asset. Finding a grid connection is only half the problem. Generating the actual electricity is the other. AI data centers require 24/7, 365 uninterrupted reliability to prevent catastrophic computing failures. To guarantee that constant baseline of power, tech giants are bypassing the clogged public grid entirely. They are directly funding and signing long-term contracts with nuclear power plants, which provide continuous electricity and vast cooling water resources. Some companies are taking this a step further. They are physically building new data center campuses directly adjacent to existing nuclear cooling towers, drawing power straight from the source to avoid the transmission grid altogether. While tech firms prefer clean energy, AI demand is growing too fast to wait for experimental nuclear reactors to be built. To fill the immediate gap, natural gas and coal plants are seeing a resurgence in regions where they offer the fastest path to reliable, round-the-clock electricity. A small startup might write a brilliant AI algorithm, but they cannot finance a multi-billion-dollar power plant. Securing independent electricity generation gives the massive tech platforms a physical advantage that smaller competitors simply lack the capital to replicate. For investors, the electricity grid operates like a toll road. No matter which tech company builds the most popular AI model, every single digital query acts as a microtransaction, paying the underlying infrastructure owners. This stretches all the way down the supply chain to equipment manufacturers. The companies building gas turbines, switchgear, cooling systems, and high-voltage cables are seeing their order books fill up as utilities scramble to expand grid capacity. However, not all electricity companies capture this money the same way. Regulated utilities earn a guaranteed return on newly constructed infrastructure, assuming regulators approve the costs. Meanwhile, independent merchant power producers sell electricity into competitive markets, allowing them to capture profits when localized demand pushes wholesale prices higher. Trying to predict the single software app that will dominate the AI industry is incredibly difficult. Supplying the physical equipment and electricity that every single competitor requires offers a much more predictable business model, but this industrial boom carries significant financial risk. If new computer chips become vastly more energy efficient, or if the massive revenue expectations for AI fail to materialize, electricity demand might not match the current aggressive forecasts. If a utility spends billions upgrading substations and power lines for a promised data center, and the tech company suddenly cancels the project, the grid is left with stranded assets, expensive infrastructure sitting completely unused. This sets the stage for a fierce regulatory conflict. Regulators are now debating who absorbs those losses. Utilities and consumer advocates are pushing for strict cost recovery agreements to ensure that if a tech giant backs out, ordinary households are not forced to pay the bill through higher monthly rates. The ultimate winner of the trillion-dollar artificial intelligence race is the company that controls and profits from the underlying power cord.